Okay guys and girls, welcome back to another tutorial on chemistry. We've covered quite a lot, and now what we're going to be doing is we're going to be applying our knowledge of ionic equations and applying it to a situation. What we're going to be doing right now is we're going to be looking at trends in group 1, its physical properties, and what we should observe when group 1 elements react with water. So group 1 elements, looking at back at the periodic table, are here, so where the number 1 is, and it goes all the way down to the bottom. So it starts with lithium, then sodium, potassium, rubidium, cesium and francium. Now I've already done a live demo of this, and it was with a live year 9 class. It was at the end of one of the school terms, and so I thought, why not do a practical? So I'll put that in the description below. Have a look at that so you can see what I'm talking about in reality, so it's not just some kind of abstract thing that I'm saying. So what I've done here is I've drawn up a table with physical characteristics, how we store it, and the observation when you're reacting those group 1 elements with water. Now at any point you can pause it and make notes, but I'm going to go through them in any case. So number 1, we'll start with their physical characteristics. So how do they appear in the first place? So number 1, what you would notice if you were to do this is that the top of group 1, so that's lithium, is relatively tough to cut. But as you go down that group to sodium, potassium, and go further down, what you'll notice is that it gets even easier to cut. It gets very easy to cut, in fact. Also, when you remove it out of its storage conditions, now it's stored in oil, and the reason why it's stored in oil is because the group 1 elements are very reactive. So we store them in oil to prevent them from reacting with air or water. So that's why they're stored in oil. But anyway, once you remove them from the oil, they're quite dull to begin with. But when you cut it, so when you cut through it, and like I said, check that video out, it's linked below, they become very shiny. But this shine disappears quite quickly as well, as it reacts with the oxygen in the air. So that goes to show just how reactive group 1 elements are. So the question is, well, what do you see when you're reacting the group 1 elements with water? Now the way you can do this is quite interesting. What you do is you take some water and you add some universal indicator to it. Now water is pH 7, so that means it's neutral. So if water is pH 7, it will give a green color when you add the universal indicator in. When you add the universal indicator in, the water will turn green, which indicates a pH 7. So pH 7 is right in the middle. Just in case you don't know, pH 1 to 6 is an acid, pH 1 being a strong acid, pH 6 being a weak acid, pH 7 is in the middle, and then 8 to 14 are all alkalis, 8 being a weak alkali and 14 being a very strong alkali. Now anyway, once you add in any metal, so let's go with lithium, then what you'll see, number 1, is that the water, the universal indicator, changes from green to a blue purple color. That's because one of the things that's being formed is a hydroxide, which means that an alkali solution is being formed. So what other things will you notice? Again, watch that video because it'll make more sense. What you'll notice is that the metals fizz, right, and they form bubbles and they float on the surface. Now group 1 metals floating on the surface is quite weird, because you expect metals to be quite dense and they'll sink down to the bottom. However, group 1 elements, they end up floating and fizzing, and they give off a lot of gas. That gas that's produced is hydrogen gas. So one other thing you'll notice is lithium is reactive, but when you compare it with all the other ones, it's not as reactive as the others. So here's lithium right at the top of group 1. Right, so here is lithium. Lithium is not as reactive as sodium. Potassium is more reactive than sodium. Rubidium is more reactive than potassium. Cesium is more reactive than rubidium, and francium is more reactive than cesium. So what we're showing here is a trend. The trend is as follows. The further you go down, So the further you go down the periodic table, or sorry, the further you go down group 1 elements, the more reactive they become. And of course, we're reacting them with water. So the general word equation is whatever the name of the group 1 metal is. So group 1 metal plus your water will make a metal hydroxide, which is what makes the solution alkali, plus hydrogen gas. So for example, my group 1 metal is lithium. I'm adding it to water. It's going to make lithium hydroxide, and it's going to give off hydrogen gas. Now this one here, this is why the water, so if you remember, the water is neutral pH, so when you add the universal indicator in, the water would be green. So let's give it a green color, why not? And however, once these two have reacted, once the lithium has reacted with the water, the universal indicator will change into a blue/purple color, right? And that's because an alkali solution is being formed. Now this one here, this hydrogen gas, is highly flammable. So let's go and put in a kind of fire color for hydrogen, and we can test for this, but I'll talk about that later. Okay, so if my general equation would be something like this: lithium, so that's my first group 1 element, plus water makes lithium hydroxide plus hydrogen. If that's my general equation, then what I want you to do is to pause the video and write down an equation for the reaction of sodium and potassium with water. So do sodium plus water first, then potassium plus water next, and then so pause the video, have a try, and then unpause it, and I'll give you the answer. So the answer is as follows, and see if you've got it right. So with group 1 element, what you would have is, and I'll write it down as well, what you'd have, because so we've done lithium, so I'm going to skip lithium. What we'd have is sodium plus water, that's my plus sign, plus water makes sodium hydroxide, right, plus your hydrogen gas. And with potassium, it's going to be very similar. So it's potassium plus your water, because that's what you're reacting together, which is going to make potassium hydroxide plus your hydrogen gas. And you can go on, so that's the plus sign, sorry, plus your hydrogen gas. So you can go down, and the formula for each one of these in group 1 would be exactly the same, right? So that's that. Now the next question is, well, how do we write this down as an ionic, well, as an equation, as a chemical equation? And it'd be like this. It'd be lithium, so that's Li, plus water, because water is H2O, and this arrow means makes. So when you react lithium with water, it will make lithium hydroxide plus your hydrogen gas. And now the simplest way to remember how to balance group 1 element reacting with water is simple. So you put a 2 in front of the lithium, a 2 in front of the water, and a 2 in front of the lithium hydroxide. Now here's the question though. So we've covered how you balance it. It's quite easy. So the hydroxide bit gets a 2, and everything on the reactant side gets a 2. So anything on the left hand side of this arrow, guys, is called a reactant, and anything on the right hand side of this arrow is the product, just so you know. So we've covered how do you balance this. It's very simple. It's 2 lithiums, 2 waters, 2 lithium hydroxide. So for sodium and potassium, it'd be the same. It'd be K plus H2O makes KOH plus H2, and the 2 would go in front of the K, the 2 would go in front of the H2O, and the 2 would go in front of the KOH. But here's the question that I want to answer first, is why is this LiOH? Why is it not, for example, Li small 2H? Oops. Why is it not, why is it LiOH? Why is it not Li small 2H or Li O little 2H, etc.? So let's cover that. Okay, this has to do with this has to do with the ionic bonding bit that we covered previously. Okay, so if we take group 1 right? So what we know about group 1 is that it's a metal, right? So this is the lithium in group 1. We know that when lithium loses, and it's got one electron in its outer shell, right? You know it's got one electron in its outer shell because it's in group 1. So it's going, because it's a metal, it's going to lose that electron, and so that will have a charge of +1 once it loses that electron. Now we know with water, right, what we can do with water is we can split it up into ions, okay? And when we split water up into an ion, we can get OH minus, so that's our negative ion. Remember, our negative ions are called anions, and we've got our H plus. When you add these together, it's H2 and O. So that's how we can split water into OH minus ion and a H plus. Now if you look at this is a positive ion. It's going to react with this negative ion, negatively charged ion, and this negatively charged ion, OH minus, has a charge of -1. So if we think back to one of the earlier tutorials I did on ionic bonding, check it out if you've forgotten, and we join these two together, remember, if it's just a plus, that represents the number 1, this represents the number 1, and so when we join them together we swap the numbers over, but in this case they're both 1, so it's LiOH, because the number 1 goes from here to here, and this number 1 goes from here to here, and it's LiOH. Let me just give you another example now. Magnesium is in group 2, right? So if we were to react magnesium, which is in group 2, with water, with H2O, right, what would be its formula? Now let's think about this. So this really, I want to emphasize this because this is what chemistry is about. It's about understanding what the products are when you react two things together. So if we've got magnesium, magnesium is a metal because it's on the left of the stepped line. It's in group 2, so it'll have 2 electrons on its outer shell. When it loses those 2 electrons, because remember metals donate electrons, it'll have a charge of 2+. Now you know we can split hydrogen or water, sorry, into its 2 components, OH minus and H plus. Now for whoever's thinking, well, why doesn't this magnesium ion react with the H plus? It's because opposite, the same charges, so this is a positive charge, this is a positive charge, they will repel, they will not react together. So anyway, let's react this positive charge with this negative charge, the cation with the anion, cation positive, anion negative. And so what we have is Mg2 plus OH minus, swap the numbers around, right? So this number 2 is going to go to the OH, so I'm going to write OH, and we're going to have 2 lots of them. And this number 1 is going to go to the magnesium. So how many magnesiums do we have? 1. So it's Mg, 2 lots of OH. I hope that makes sense to you, and I hope you realize this is why it's LiOH and not anything like this, or Li2OH, or etc, etc, etc. So anyway, what I'm going to do, I'm going to get back to what I was talking about, which was the chemical equations for this. So what I'm going to say is Li, lithium, plus water, which is H2O, is going to make, that's that arrow, lithium hydroxide, and I've already explained why it's like that, plus hydrogen gas. Now remember, the way to balance the group 1 reaction with water is simple. It's a 2, a 2, and a 2, right? So you guys pause this video, see if you can do a balanced equation for the reaction of sodium and potassium with water. Okay, so the equation would be something like this. Well, it wouldn't be something like this, it is this. So it's sodium plus, we're reacting it with our water, is going to make sodium hydroxide plus our hydrogen gas. Balance it again, 2, 2, 2. Nice and simple. And potassium would be potassium plus your water. It's going to make potassium hydroxide plus your hydrogen gas. And so what would you notice? Again, let's balance this one. So let's pick a different color. Let's go with this blue. So it's 2, 2, and 2. Now, what you will notice, like I said during this, is that you're going to notice bubbles being given off. You're going to notice that it's fizzing.
you're going to notice that it's actually the metal is reacting on the surface of the water, so it's going to be floating. It's an exothermic reaction, so it's going to give off heat. In terms of the pH, you're going to notice that it's going to go from pH 7 neutral, which is green when you're using universal indicator, and it will turn the universal indicator will turn a bluey color, because of course you're having this alkali solution being formed. Now finally, the state symbol. So what states do they exist in? So as you can see from the video that you should watch, that's linked in the description, the metal here is a solid, water is always a liquid, it's going to form a solution, so this is aqueous solution of lithium hydroxide plus your hydrogen gas. So that's what the gas stands for, the fact that it's a gas. Aqueous here means that it's something mixed in water, so this lithium hydroxide is going to be mixed in water, so we call it AQ for aqueous. Water is always a liquid, lithium is the solid. So in this case, the sodium would be a solid, the water would be a liquid, this is going to be an aqueous solution, so AQ, and this is going to be the gas that's given off. Now there's a couple of more things. Each one of these gives off a unique flame color. So if you were to light it, as I've done in my video, I'm sure I did it, lithium will give off a red flame, right? So each metal will have its own unique color. Sodium gives off a yellow flame, and potassium gives off a lilac flame. Final thing, how do you test for hydrogen? So that's supposed to be a H, that looks awful. Hydrogen, if you collect hydrogen gas in a boiling tube, right, so collect the gas in a boiling tube, then light a splint, the hydrogen will make a squeaky pop. Okay, so the next question is, well, why does the reactivity increase down the group? That's the only question that we're left with. Let's see if we can answer that. Right, so the question is, why do the group 1 elements get more reactive as we go down the group? Let's take lithium, which is right at the top of group 1, and guys, you will need your periodic table for this. So lithium is 7 for the top number, 3 for the bottom number, and of course potassium, if you look at your periodic table, is 39 for the top number and 19 for the bottom number. Right, so remember, the bottom number represents the number of protons, which happens to equal the number of electrons, okay, and this is the total number of protons and neutrons. Anyway, we're interested in the bottom number, because what we're going to do is we are going to draw out the electronic configuration for lithium and potassium. So lithium is something like this. Well, not something like this, it's exactly like this. So lithium has 3 electrons, so we're going to give it 1, 2, remember it can only have a 2 maximum electron in the inner shell, and then 1 on the outside. Now because it's in group 1 and it's got 1 electron in the outer shell, I'm happy that I've done this correct. So that's a way of checking it. Let's do potassium now. Potassium has 19 electrons, so it's 2 in the inner ring, right? It's 8 next, because the maximum in every other shell is 8. So 1, 2, 3, 4, 5, 6, 7, and 8. So that's 10 in total, 8 plus the 2. Let's give it another ring, and this is getting ridiculous. So here's another 8, so 1, 2, 3, 4, 5, 6, 7, and 8. And one final one, so that's 8, 16, 17, 18 in total. 1 in the outer shell, which makes it in group 1 as well, because remember the group number corresponds to the number of electrons in the outer shell. So the code for this is 2, 1. The code for this is 2, 8, 8, 1. Now remember, so the question becomes, well, why is it this one more reactive than this one? So the key things to remember really is that, number 1, these are metals. So these are metals, right? Number 2, the metals give away or donate Right, so that's donate electrons. Now, what you got to remember is this positive bit, this nucleus bit here, is positively charged. Right, so the nucleuses are positively charged, whereas the electrons are negatively charged. Right. So what you got to think of to yourself is, well, which one has the greater attraction? Is there a greater attraction between this distance here, or greater attraction between this distance here? Well, of course, it's easier for there to be attraction here. So the attraction here between the nucleus and the outermost electron is stronger, right, because the distance between them is smaller. So the distance between the positive center and negative electron is smaller. So that's why, number one, this is less reactive. The second reason is, if you look here, so I'm going to change my color up a bit. So if we look here, look at how much shielding this one has. So between the positive center and the outermost electron, because this is the electron that's going to go, remember, look how much shielding we've got. We've got 1 shield, 2 shields, 3 shields, 4 shields. So the force is protected by all this shielding. How much shielding do we have here? 1, 2. There's not much shielding between the positive nucleus and the outermost electron. And so why is this less reactive? Because there is less shielding, and so so it is difficult for an electron to be lost. And again here, so why is this more reactive? Why is potassium more reactive? Is because, number one, the distance between the positive nucleus, so the positive nucleus, and the outermost negative electron, distance is big. So there's less, let me just write it here, so there is going to be less attraction, so the electron is easier to lose. So electron is easier to lose. And the second reason, so let me just change my color up a bit. So the second reason why this is more reactive, why potassium is more reactive, is because there is more shielding caused by the electron shells. Remember, these are the electron shells, so you got 1, 2, 3, 4 electron shells caused by the electron shells, which means there is less attraction between the positive center and the negative most electron, and so it's easier to lose that electron. And that really concludes the trend and the reactivity series and the patterns that we see. Now finally, I'm going to say again, watch the video down in the description, because we actually go into you can actually see for yourself what I was talking about. If there are any questions, just ask them below.